oscillation I will not get.
Yes, but yes, when you are looking for say double beta decay, neutrinoless double beta decay experiment, where electron number is violated by 2 unit, and you want to write down this m beta beta, right? Then basically you need to take into account these phases.
Actually, my confusion is you get the simulating phase with that type of neutrino only in 3 flavors, right?
Yes.
But suppose you have 2 flavors and both the flavors are Majorana flavor, then even in 2 flavor you can produce differentiation from the Majorana. Is it correct?
In 2 flavor, since in oscillation there is no thing, but when you write down the double beta decay, the mass that you are measuring from neutrinoless double beta decay experiment, then definitely this phase will come into the picture.
But that
is Majorana phase, but you can't disentangle because it will change the the number of event rates in the double beta decay process, depending on whether it is 1 phase or 2 phase or 3 phase, depends on how many flavors you have. But you can't disentangle that the contribution is coming from Majorana phase or contribution is coming from Dirac phase.
but both the phase can be simultaneously available?
Yes, yes. But what you measured is not this phase. This phase can be separately measured only in oscillation experiments. But in double beta decay experiment, okay, and there can be cancellation also due to these phases. Okay, when these phases from Dirac type or Majorana type is there, but again you need to understand that when I am talking about neutrinoless double beta decay picture, you demand lepton number violation. So mostly then you are talking about Majorana type neutrinos. Okay, so then basically you bothered about the Majorana phases in the picture, because you are talking about explicitly Majorana type neutrinos, right?
So you might ask him, in case of Dirac neutrinos, you see this delta is entering the oscillation parameters. So this is not redundant.
This is not redundant.
But in case of Majorana, so you are putting in a diagonal phase matrix, so it is
redundant in oscillation.
So he is saying, suppose you have a Majorana case, so why? Okay, can you insert can you parameter in kinds of this Dirac circuits?
You can parameterize that, but you see, you need to see in which process I can feel their presence. And the immediate answer is the double beta decay process, where you demand that neutrinos are Majorana type, and you can feel the effect of this alpha 1 or alpha 2 there. But in oscillation, whether this is Majorana or Dirac, that doesn't matter. What you measure is the difference between neutrino probability and anti-neutrino probability, and that is caused due to some CP violating phase. But that you can't answer, that is basically assigned to this Dirac CP phase, because in calculation of the probability, when you fit the data, they will not be coming into the picture. Alpha 1 and alpha 2, they will not be appearing in an oscillation probability. So what you fit is this delta. But when you fit your neutrinoless double beta decay event, if you see some number of events, and you go back to the theory that how I can get this number, in there these phases will also enter. You can put them 0 or you can include them. Okay.
So you might wonder why this Dirac phase cannot be put in a diagonal phase matrix.
No, that is
so
not.
That will not put it into unitary. So
right.
In the first slide you have shown this oscillation. This picture. No, go forward. This oscillation picture, right? So this oscillation will depend on the combination of L by E.
Yes.
So suppose I fix my E.
Okay.
And I change my L.
Right.
So if I put my electron in different L, then there will be some L where I will see new mu, and there will be some L where I will see new E.
Excellent. You are correct.
But suppose I put my delta in a region where I should not get either new mu or new mu, then what should I see in that region?
No, Arpon, you see, whenever you put a detector at some place, you know the L and you know the E. There, basically, you will be bothered about where from they started the journey and where you are detecting them. So whenever you are detecting them, whatever when they reach this 2F packet reach to your detector, nu1 and nu2, they will again collapse with certain proportion to your flavor basis, and this probability will be finite all the time. You understand?
So is it possible we can anyway know at which point of the year they are exactly changing it?
Sure. You can, this is the game. You play with these parameters, oscillation probability, you code them, you plot them, and this is what we are doing as our bread and butter. We are basically plotting them, understanding where we should put our detector, at what energy, what baseline, so that we can maximize our oscillation probability to get those mixing parameters. Okay, so this is one of the, you have to optimize your LE as well as the oscillation channel, but then there is another story also. As in collider, you have some signal, you have to know your background, because it's a neutrino experiment. You will get 2 events per day, where they will get 2 billion or million events. Okay, so it's totally different ball game. One background can kill you, so that's why every neutrino experiment is underground. Okay, so Darpon, should I proceed? So this is your 3 flavor picture, and as far as this reactor angle is concerned, which was measured in 2012, this information mainly came from this reactor experiment. Now in reactor you produce only nu-E bar. Okay, so this is the neutron decay. Okay, you produce this nu-E bar, and you look for the disappearance of nu-E bar. You put your detector at certain distance, it can be 1 kilometer, 2 kilometer, 100 kilometer. As you are mentioning, your probability will be different, right? Because you know the probability expression. This is the survival. So you put E, this is bar, but we are assuming this Lorentz invariance. So this theta, this mixing angle, we are assuming that this is same for neutrino and this is same for anti-neutrino. Who told you? There is no obvious reason, but yeah, we are fan of Lorentz invariance. But I can write a paper, and you can also write a paper, and it has been studied, because we are entering into the precision phase. You are measuring these parameters very precisely, and always producing P bar is difficult than P, right? Antiproton production is very difficult than proton production. So here also, you have most of the experiments, neutrino experiments, not anti-neutrino experiment, but now we have enough data from anti-neutrino channel also. So people are doing different fit. They are only taking neutrino data, fitting with their model, and you get, say, theta 45 degree. I go take only anti-neutrino data, and if I get the angle 42 degree, then definitely I have to define theta bar, if they are very precise, if they are not in the error bar. So then you have to ask whether Lorentz invariance is obeyed in neutrino oscillation or not, in neutrino case. So there is an urgency, this is a need, that you want to measure these parameters which are fundamental, separately using neutrino data, separately using anti-neutrino data, so that you can really confirm that okay, everything is working together. Otherwise there can be departure. This delta m square can be different for neutrino and anti-neutrino. Even for 2 years, MINOS, when they run in neutrino mode, they give you some data. When they ran in the anti-neutrino mode, they gave some data, and when people fitted, there was 2 different thetas they are getting, 2 different delta m square they are getting. And there was a speculation whether there is a Lorentz invariance is maintained. Okay, so you can ask this kind of question, new physics basically, in oscillation experiments. Okay, so good thing is that now in 3 flavor, you have these 3 mixing angles, and you have this phase. So forget about the Majorana phases, as I told you that they are not coming into your picture. So you have these 3 angles and 1 phase. So the job boils down to measure these 4 parameters which are part of your U, the big PMNS matrix. So this is your game. Okay, you have to measure them, and most beautiful thing, that who told you that you have to multiply these 3 matrices in this way? Nobody has told you. So So if you can put this here, this here, this here, this here, your model should work. Okay. So your physics should be independent of your parameterization. But this is a historical thing that following the success of VCK, if you go to PDG, the parameterization they took for the quark sector, in the neutrino sector, if you see and go back to 90s paper of oscillation, they followed that approach. Okay, and that's why now we are habituated to take this parameterization, but so that you can match the analogy between quark and the lepton sector. This is just historical. Nobody has forced you that you have to take this parameterization. But now if you take a different parameterization and if you feed the same data, as I told you, your physics should not be dependent on your parameterization. So you can calculate that, say you are calculating a probability nu e to nu mu with this parameterization. Now you calculate the same probability but change the location of these matrices. Up to a minus sign or plus sign, things will be same. Okay, you can convince yourself. Okay, but here another historical point was, first people started getting the solar data, so they were working with this angle in a two-flavor framework. And in two-flavor there is no phase, so they didn't bother to introduce any phase. Then Super Kamiokande, they started giving atmospheric data, so you started playing with this block. Again you are in two-flavor, people didn't bother to put any phase there. But then when these two sectors were precisely measured, people bothered. Okay, you can see how nature satisfies or follows your attempt. The tougher one will be observed later. So these were big, so you can see their big effect early, but θ13 was small, so you had to wait. And when you discovered θ13, people immediately saw, okay, so there are three flavors, θ13 has to be there as a bridge between solar and atmospheric. Okay, and you can immediately put a phase over there. Another beauty, if θ13 would have been 0, immediately this phase will be vanished from your parameterization. So that's why people club this θ13 and delta together. Okay, this is just a historical thing basically. When people are getting data, they were just fitting in this way, and then they put this intermediate Euler mixing and the θ13 with the phase. Okay, but beauty is, benefit of this parameterization is that if you measure what is the nu2 component in nu e, which is ue2, right? And what is the nu1 component in nu e, which is e1, and take the ratio, you measure this quantity θ12. So this is your physical quantity that you want to measure. Whatever parameterization you take, but ultimately you are measuring this value, this mixing element, ue2 or ue1. How much nu2 is there in ue, how much nu1 is there in ue, and you take the ratio, you get this θ12, the physical measured variable. Okay, independent of parameterization. This is the beauty. Similarly, θ2.3 and similarly this θ13 also. Okay, so this is simply related to flavor components of three mass eigenstates. Okay, this is a nice beauty of this parameterization, and this is the general expression. If neutrinos are traveling in vacuum, this is the general expression you need to use to calculate the probability, and it can be done in pen and paper. No computer is needed till this point. Okay, you expand this u is the three flavor, this product of these three, and these are the frequencies which are defined here. Now there are three flavor, so there will be two independent mass splitting, delta m12 square and delta m13 square or 23 square. So the job is, you have these four parameters and you have two splitting. So you have these 6 parameters you want to measure in oscillation experiment. This is what we are discussing today. So this is the job. So this is your u. Again, you can take a look, and this is the full u, and this is the probability just we discussed. So you can do it on pen and paper. But game is complicated. and there you need your laptop or desktop. So when neutrinos passes through matter, because you know if you are looking for a solar neutrino, supernova neutrino or atmospheric neutrinos, even if long baseline neutrinos, they are traversing certain part of matter. That matter can be a part of sun, atmosphere, your earth. And the beautiful thing of this MSW resonance, which DP discussed, I just want to summarize that when you have a neutrino, it can be nu, mu and neutron. But in matter, you have electron, neutron and proton. Now with nu, electron can interact with nu when you are traversing, and you can have both neutral current and charge current with W and Z. So if that is Z, if this is W, this is special for electron or nu, because in matter you don't have muon or tau. If there would have been mu or tau, then nu mu and nu tau also, they will also have this process. So nu is special, that since you have ambient electrons in matter, they will have this extra process which will not be there for nu mu or nu tau. Clear? It will not be there. And also you have this neutron and proton, and that will have with both nu mu and nu tau, they will have neutral current interaction. But the potential will be same. So it will be like again a common phase in the propagation, and you can forget about that. So the beauty is that you have only electron in the matter and you have nu which will fill that potential, and that is the extra piece which changes your total idea of neutrino oscillation. This is the matter effect. So it's like neutrino is traveling, and it is just neutrinos are having coherent forward elastic scattering. Coherent forward elastic, all the three words very important when you want to calculate this. Neutrino remains neutrino, they don't change their type, they don't lose energy. So elastic, forward means you can add up this potential. So neutrinos just you are like you are just playing a car, you are going here to some part of Odisha, and your car is facing the bumpers on the road in the same fashion, and when you reach the other place, some part of your car is broken. So this is the effect, MSW effect. So neutrino is gathering some effective mass. Okay, coherent, has to be coherent, forward and also elastic. So when neutrino scatters with electron, that can be a backward scattering also. So when you calculate the potential, that half factor comes into the picture. Okay, because you need to only create a forward contribution. Okay, so this process is happening for nu.
How they acquire mass?
Huh?
Due to this.
This is effective potential, so effective mass. Yeah.
So, but practically, one can measure this probability of anti-neutrino oscillation through matter?
Very good question. So if you have nu bar and you have electron, okay, so then you don't have positron. So that's why your matter is not CP symmetric. So you take the difference and then you measure the difference. Okay.
So practically, an anti-neutrino doesn't travel through matter, right?
Antineutrino travels. You create antineutrino in your lab from pi plus, pi minus decay, mu plus decay. You have antineutrino. You can create antineutrino.
But doesn't it annihilate while traveling through matter?
Why they will annihilate? Because it is a neutral particle with whom you are thinking that they should annihilate.
It must be coming at
It is not positron or electron that they can annihilate.
But antineutrinos must be coming at this neutrinos.
Antineutrinos
Must be coming at this neutrinos.
coming at,
They are antiparticles.
yes, but why they will annihilate? How? Both are neutral particles.